Hello, this is Dr. Bricker here with a description of the Newton's second law P&W lab. It's the next lab that we're going to be doing. It's a couple of objectives here. Calculate the acceleration from displacement and time. So we'll do that. This is sort of old stuff to us now. This is using kinematics equations. And then a couple other objectives to find the relationship between force and acceleration for a given mass. So think Newton's second law. And then to find the relationship between mass and acceleration for a given force. So the second bullet point here, we're keeping the mass the same and finding the relationship between force and acceleration. And in the third objective here, we're keeping the force the same and finding a relationship between mass and acceleration. Okay, the lab looks sort of like this. So read through all this. Here's a cart, and there's a fan here. And in the beginning, we're going to be able to get this fan going, but it's attached by a spring. So this cart here is going to move down an air track, so we're assuming there's no friction, powered by this fan. And the reason that you're seeing this top view is here. We're going to turn on the fan, it's going to stretch the spring, and eventually we'll be able to measure the force. And then when you cut the string, the fan remains on, and the mass accelerates down the track here. So let's take a look at and see what this looks like. Okay, so it's kind of a big picture. I'm just going to hit play. So by the way, you can change the mass and the fan force. Now, before we do that, the fan force 3 doesn't mean there's 3 newtons of force. It just describes that it's the third setting here. Like, for example, we've got fan force 1 through 5. That doesn't mean 1 newton, 2 newton. It just describes the fan force. And then you can change the mass of the cart here too. So I'm just going to leave it as this one. And hit play. So the fan is on. So the force is there. It's not moving because it's attached by this string and then the spring here. And then you could hit play. And then the fan accelerates down the track. So from kinematics, we could actually figure out how much the acceleration is. So we're assuming that the cart is starting from rest and accelerating down the incline. So let me back it up slowly. That's where it's cut. Okay, so right there, the initial velocity is 0. So we can get the acceleration by using some tools here. So what do we have? We have this meter stick here. Pick a nice convenient spot. I'm just going to put it maybe on maybe the front of this cart. And you can do this a little more carefully than I'm doing it. I don't have my reading glasses on, actually. Maybe I should do that. So yeah, if you need reading glasses, put them on for this step. Okay, so I'm putting this at the 0 mark, the very leading edge of the cart, and I also have a stopwatch here. So I can reset it to 0, and then I can let this thing go down the track. So advance it frame by frame if you want. So 0.0083 seconds. It's moving, and there we go. So we're starting at t is equal to 0, and the x coordinate is 0. Now we don't want the person's hand to touch it. So maybe right about, I'll just stop it at a nice convenient thing. Okay, so that looks like about 80 centimeters. I'm looking at the leading edge here. 80, it's here, 81, 82 centimeters in 0.9333 seconds. And it's accelerated the whole time. So we can use kinematics to figure out what the acceleration is. Let's see how we can do that. Okay, so we're assuming the initial velocity is 0, right after we cut the string. You can measure the time, and you can measure the displacement. And what we're trying to figure out is how much the acceleration is. So you've got several kinematics equations to look at. So just to refresh your memory, final velocity is equal to initial velocity plus AT. I mean, that has acceleration in it, but that has final velocity, initial velocity. So that one doesn't work for us. We also have this one, final velocity squared is equal to initial velocity squared plus 2a delta x. This one also has acceleration in it and displacement in it. It doesn't have time, which we will be able to measure, and it has final velocity, which we do not know the final velocity. Third kinematics equation, delta x, initial velocity times time, plus 1/2 AT squared, and we're assuming we're starting from rest, so this term is actually 0. So let's look at this. Delta x we measure, the time we measure. The only thing that you don't know in this equation is the acceleration. So you'll have to do a little bit of algebra, but you can use this third one to calculate the acceleration, just using kinematics. Now, looking back at the first two equations, you might say, well, can't we get the final velocity? Isn't it just distance divided by time? And that's not true. What that would give you would be the average velocity, right? Because it's accelerating the whole time. So if you just did distance divided by time, that is not the final velocity. Distance divided by time is the average velocity. So you can't really use the first two. You can get the final velocity because it's twice the average velocity, it turns out. But from this one, knowing delta x, knowing the initial velocity is 0, you could use this equation to calculate the acceleration. You'll have to do a couple of steps of algebra, but you can do that. Okay, let's go back to the experiment. Okay, so why was I showing you this? Because you'll have to answer some questions down here. So, force 3, mass 800 grams, we actually did that one. So you'll read through here. You have a couple of submissions for this one. So we've got some multiple choice going on. You can have 2 chances to get this one right. Question 2, let's apply kinematics. So I sort of just ran through how to do that. You should be able to use kinematics and calculate what the acceleration should be. So be careful, these answers are in meters per second squared. This meter stick here actually measures in centimeters, so be careful with the units. Okay, good. So force exerted and the glider. So you've probably noticed that you can vary the fan force in the video. Let's look more closely at the forces exerted on the glider and how to measure them. So advance the video until just before the ribbon is cut, but after the fan is turned on. While the fan is on, the spinning turbine exerts a force on the air to the left. Initially, the glider is attached to a spring with the fan on. While the glider sits motionless just before the ribbon is cut, which of the following statements best describes the horizontal forces acting on the glider? So just the forces on the glider. Okay, so think about that. Think about making a free body diagram for the glider. So that's when it's not moving, it's sitting motionless. So there is no net force then, right? There's a turbine force on the glider. I don't want to say too much. One way, something's holding it back the other way. So, think about that. Okay, now, actually, maybe think about question 2 first, because we're looking at the free body diagram. Okay. So this interactive includes a spring scale. It looks like a ruler with newtons for units. When you deploy it, it places the tool in the top view of the glider. This measurement device uses the amount that the spring is stretched to measure the force. So it's basically a spring scale. Use the spring scale to determine the value of fan force 3. Let's take a look at how we could actually do that. Okay, so I'm back to the glider. It hasn't been turned on yet. The spring is not stretched. We'll use this to measure how much the force is. So the amount that this is stretched is proportional to the force. So we could actually measure the force. Let me advance this a little bit so you see what it looks like. Okay, I'm advancing it slowly. And I want to get this into position. So 0 force, I'm just going to use the leading edge of the spring here. And then once you turn it on, this fan on, Okay, there we go. It's going to stretch. So the motor has not been turned on yet. I don't want to miss it, so okay. Now it's being turned on. The string hasn't been cut yet. This is coming into closer view. Okay, so the spring stretched, and I looked at the leading edge of it. It was here at 0 before we turned it on. Now we turned it on, and the spring stretched. It looks like we have about 1.5 newtons then, right? Because I measured the leading edge. A little bit of estimating going on here, but I'd say it's about 1.5. Let me back it up just to make sure I'm measuring the same spot. Yeah, that was the leading edge of the spring here. You can pick whatever spot you want to. And then I turned it on, stretched out to about here or so. Okay, and that's before the string is cut. And then eventually the string is going to get cut. So this is the device that tells me how much the force is. And then once you cut the string, the fan stays on so that we still have that much force propelling the cart down the track. Okay, so let's get back to the lab. Then that's how you measure the force. Okay, back down to here. Okay, excellent. That's kind of a freebie for you if you're watching this video. And then experimental questions and procedure. So before you begin, write a hypothesis for each experimental question. What do you think will happen and why? So a statement something like that. The acceleration of the glider will blank when the force of the fan blank because. And something like the acceleration will increase when the force of the fan increases because, something along those lines. Okay? Or maybe you don't think that. Maybe you think it'll decrease. Whatever. Or maybe you don't think it'll matter. Whatever you think. But think about Newton's second law when you do that. And then we'll collect and analyze the data. Okay, so create a data table. You're good at that now from the first couple of labs. So create a data table and graph for the first question about the relationship between acceleration and force. Okay, so in this one, you don't want to do anything with the mass, right? You're just looking at the relationship between acceleration and force for a given mass. And I'll leave this part up to you. You know what the mass is from the settings there. Okay. Good. So this is really Newton's second law, isn't it? F is equal to something times A. So the slope is whatever the something is. Okay. And then this table and graph are for the second question. How does acceleration depend on mass? So in this one, again, I don't want to say too much. You want to keep the force the same and see what happens for different masses and that sort of thing. Okay. Okay, and then for this part, we are plotting, as it says here, your graph should have acceleration on the vertical axis, so you'll need to add columns to calculate the acceleration. The horizontal axis should have 1 over mass, so be sure to include a 1 over mass column here. So again, here you're keeping the force the same and changing the mass. So why are we plotting 1 over mass? Let's take a look at that. Okay, so it says here to plot acceleration here, meters per second squared, and 1 over the mass here. So this would be 1 over kilograms, unit-wise. So why is it 1 over the mass? So you know from Newton's second law, F is equal to ma. So if I solve for the acceleration would be F over m. So if you think about slope-intercept form, y is equal to mx plus b. I put the m in quotes there because that's the slope, that's not the mass. Okay. The form of this is when you have y, y versus x. Whatever comes in front of the x is the slope. So it's the same thing over here. This acceleration is sort of playing the role of y. It's on the vertical axis here. and we're plotting 1 over m on the horizontal axis, so the force should give you the slope, right? So this, if you want to think about it like this, this is F and then times 1 over the mass. So A is kind of like y in the slope-intercept formula, and then 1 over m is kind of like x. So then the force gives you the slope. Okay, so let's go back to the experiment. I want to say a couple other things about how you get the acceleration. Okay, so I'm back to the part where we're looking at acceleration and force, and we're supposed to plot force, make a graph of force, which you measure directly, and the acceleration, which you can calculate. So think about what we did in the first part. You can get the acceleration because you know you'll be able to measure delta x and t, right? So then from that, using that kinematics equation, you can get the acceleration. So you could have a column here for like delta x, another column. So let me just, you'll have to have a column for force, and then I would just do something like column name delta x, units, maybe you want to convert it to meters, centimeters, however you want to do it, and I'll just call this x. Let me add another column, insert column to the right, and then time, units, seconds, variable t. So from that you can calculate the acceleration. So let me add another column to the right, and then I can call this one acceleration. I spelled it right. Acceleration, units, I'm going to do meters per second squared, variable a. And then from delta x and t, you can calculate the acceleration. Now you could do it on a piece of paper manually and just enter the numbers here, or you could let this program do it for you. So if you click the 3 dots here, let's see, change column formula, you could enter the formula here, however you want to do this. So like, I don't want to give too much away. You could use the stuff over here, and put the formula here, put submit, and it'll do all the calculations for you. Okay? I don't want to, again, give too much away, but that's just something that's there for you. If you don't want to have them do it for you, you could just do it by hand. Calculate these accelerations by hand. And then on this one, you'd have also the force. Newton's F. And then you're going to graph force, vertical axis, and the acceleration here. Now you do a similar thing down here. It's just you keep the force different, and then you'll have different masses. And again, you'll have to have a delta x and a t column and an acceleration column. And then here, you're plotting acceleration versus 1 over the mass. So actually, if you have a mass column, you should have a 1 over mass column. So you'll have mass, 1 over mass, delta x, t, and then acceleration. Okay? Excellent. And then some general conclusions down here. How do you account for the percent differences? Remember, this is not a perfect lab. There's some estimating going on about, delta x, things like that. How would you change the experiment to get more accurate results? Pretend it's your job. How would you, your job was to measure these different things. How would you change the experiment to get more accurate results? And then a little summary here. So you don't have to write a whole page, but make sure that you use complete sentences, that sort of thing, for both of these. All right, if you have any questions, just send me an email, and I'll talk to you soon.